We have a fulcrum here. Let's start from myself. And last week, with the help of Riddock and Sam, we got all the recovery state machine and write path, the preliminary support of a write path, the read path merged into master, and after that I was trying to provide the read performance of Crimson OSD, but the performance of Crimson OSD is almost on par with that of a classic OSD. So I wonder if I need to compile Crimson OSD with using the release build instead of using debug build. So I was and I ran into a problem of safe CI because it enables the ASAN sanitizer even if the ASAN sanitizer is not enabled. I haven't got a chance to do the profiling, but I will do so in the following part of this week. Yes, release with debug. That's the default setting.
From my experience,
yes.
The debug build will be much slower because there will be some extra checks replaced.
Exactly. The debug build of SeaStor is quite different than that of than release build in SeaStor. So I think it would make a lot of difference. I will redo the profiling with the release build. It again?
This is with memstore in both cases?
Yes.
But classical OSD will be affected as well, even because of extraordinary checks in our locking infrastructure.
Oh yes, true. Yes.
So were you comparing throughput or latency?
I think it's throughput. I was using the Redos bench command to test the performance.
So there's another difference, which is that, well, did you compare the amount of CPU usage? Because I believe the way you have it set up for Crimson is it's localized to a single CPU, right? Whereas
yes.
For Classic, even with the vStart cluster, I think it defaults to like 2 or 3 worker threads. So it may be that you achieve the same performance with only a fraction of the CPU use, which would be interesting if true.
Kifu, I guess you will want to use perfstat to record both for classical CEF-OSD as well as for Crimson OSD to record numbers about, for instance, few cycles burned by entire processes.
Sorry,
should give you.
What tools you are suggesting I should use to record the CPU usage?
Well, I was thinking about perfstat.
Perfstat. Oh, okay.
Also, you'd see it in HTOP. If you just run top, you'll see probably Crimson using like 1 core, but Classic probably will use 2 or 3, maybe more.
Yes.
I don't know what the defaults are these days.
By default, we have 16 threads per on SSDs.
Well, it's more.
Even more. Sorry.
I'm not sure what vStart do. I don't think vStart uses the same defaults. Although I could be wrong.
Well, I was profiling. I'm bet there is around more than 20 threads, 16 TP-OSD TPs plus 3 messenger threads.
Yeah, so
per single OSD.
You got the same throughput. That would be a big difference. Rather a large improvement. But also looking at latency would be interesting. Because that's the other guess, right? That we're doing fewer thread hands-offs, so it should be faster in that dimension as well.
I think the bench should also profiling the latency, right? If I recall correctly.
Know. I can't remember.
Okay, I'll take a closer look at it. How can test it?
I think it does.
And I will.
You can
Yes.
give it a dash T argument that determines the queue depth in Rados bench. So
Oh, yes.
presumably it does return latency. Otherwise, that argument wouldn't be that useful.
Okay. I will also ping mark to see if my methodology makes sense, and copy all of you. And I think that's me. I will keep you guys posted regarding to the profiling. Trimi, how's it going?
可夫, do you just do the Crimson OSD profiling, or you want to do some comparison? Not hear you.
Sorry, I forgot to unmute myself. I think the whole point is to compare the performance of between performance of Crimson OSD and the classic OSD. So I will providing both of them using the same approach.
Do we finish all the IO paths?
No, not really. But
how you do the comparison?
I guess
barely
really what
works.
your compare is- Oh, sorry. Go ahead.
It's just a minimal implementation to connect the messenger to the underlying memory store. So it's not quite complete or close yet. It's just a very preliminary implementation. I think the next step, the one thing we need to work on is to figure out a better methodology to benchmark Crimson OSD. Another is to understand what could be sitting in the read path or write path and add the missing pieces into read path to make it more sort of realistic comparison between make it more like a fair game between both of these implementations.
Well, that'll happen naturally as we actually implement it, right?
No, I don't
Yes.
understand what profiling you will do next step.
Well, it might be fair. So would it be fair to say that one of the main guesses as to what we're trying to achieve here is that classic OSD spends a lot of time passing stuff between threads? That's just a thing that is true. It's inefficient with locks and it's not great with memory usage. So even before we begin working on the I/O paths that actually touch hardware, there's a lot to optimize between the messenger and there before we even touch disk. So what we have so far, if I'm understanding correctly, is a messenger and a dummy backend and the beginnings of the path that connects the two. So we're trying to estimate how much faster our current version of that path is than the classic OSD path is. That way, as we begin fleshing out that part of the path to implement things like peering, recovery, backfill, actual I/O, that sort of stuff, we'll know if it becomes slower and why. Would that be fair to say?
So we are doing the messenger profiling itself. So,
in a sense, but it's not just that. It's also the handoff to the part that encapsulates the PG state, because we just burn a lot of time there in classic OSD. Like if you look at the locks involved, there are like one of them. It's kind of remarkable.
So what method can we use to just compare the PG state, something like that?
So in a sense, we get it for free by running classic PG with a memory-only backend. So then it's apples to apples in that neither version is actually doing I/O. So all we're really testing is the overhead.
So
in both cases.
Do we have the I/O path finished? Without the I/O path, how can we do the I/O test?
I think we can consider part of it finished because we can, if we pre-populate the memory store with some data, we'll be able to run random read or sequence read using the reader bench. That's what I was doing last 2 days.
Yeah, but I mean, can we use that to do the comparison, the apple-to-apple comparison profiling test?
You can argue that if Crimson OSD uses a quarter of the CPU to do the same thing, then it's 4 times faster, right? The same thing in this case doesn't include the actual I/O, but it's still useful. We do still need to actually, write the part that writes to disk. That clearly is an important component.
Well, try to think about the entire idea as a measure to verify the real benefit coming from just employing
SeaStor.
Of course, the OSD is not fully operational, it's not fully functional, but it's enough to judge whether further investing in SeaStor does make sense or not.
Yes.
Because if you think about the counter possibility, perhaps we test this and it turns out that even this version actually isn't faster than the classic OSD, even when it's only writing to a memory backend. That would be an outcome
Exactly.
to think about, right? So this is an opportunity both for us to get a baseline number that we can compare against as we actually implement the Crimson OSD, and also an opportunity to validate this strategy. That be fair?
Well, boiling down, it's an opportunity for early abort.
Yeah, exactly. Although I don't think it's possible that it's going to turn out that the classic OSD is optimal. Let me put it that way. But it may turn out that something about what we're doing now is wrong, right? It might be we made some assumption early that turns out not to be valid, so we need to back up a bit.
Yep. The entire question is whether the benefits justify the effort spent on porting everything. If there is only 5% or 10%, well, it might be not worth the effort.
Yeah. I think it's a very crucial time point for us to do the profiling, to understand what holds us from getting an optimal performance result. If it's a good, we are good. If it's bad, we need to understand what is holding us back.
And to be clear, just for reads, I wouldn't expect to see a large difference in overall throughput or latency. What I would expect to see a difference in is CPU usage. Or to put it a different way, if you ran enough throughput to actually tax the CPU in the box you're using, then you would see a difference in throughput by whatever fraction you reduce CPU usage by, right? And that's one of the goals. If the challenge is that a 32-core machine doesn't provide enough literal CPU cycles to saturate a PCI, one of these PCI Express or whatever, not fast storage devices, then our problem isn't even that we're wasting time; it's that we're wasting cycles.
Okay.
So even just finding that we've reduced CPU usage by a factor of 4 for the same throughput, that would be huge, right? Massive. Yeah. So there are a lot of dimensions on which this could be important.
That makes sense. Yes.
Although I do also expect to see a difference in latency, just not a big one.
Yes. Unless we are kept by the CPU cycles, we cannot tell the difference.
But you will. I think, unless I'm mistaken, it uses like 2 OSD thread pool threads by default, and that's not even counting the backend threads. So if you just look at HTOP, I think you're going to see if you run it for like 3 minutes and just open top while it's running, you're going to see several cores utilized with classic OSD, but like only one with Crimson, probably. Maybe 2. I'm not sure. With the alien machinery, perhaps there's an additional thread.
Okay.
But that's kind of what I would expect to see. I don't know though.
Kefu, and Samuel, Jim already sent out the messenger test result, and my side, recently I'm struggling with the other task, not pay much attention to the Crimson OSD. I hope I can finish it this week's the other task. So hopefully it is well done within this week. So no update from my side.
Cool.
Are you talking about the SeaStor messenger staged reads? Yeah, I haven't dug into this. I don't. Yeah, I need to learn about how the messaging pathway works. I'm way out of date.
Yeah, I'll take a look at the Jimpon's report. And Redux, how's it on the side?
Mostly reviewing the stuff. Idea is I plan to make also some profiling of the Crimson OSD in comparison to classical OSD.
Okay.
Right now, I'm reviewing the staging patch for Messenger.
I think we can take advantage of staged executing using it in two parts of a messenger. One is to do the encoding and decoding for take advantage of a code cache. And another thing is to batch the write, as we discussed over another PR, to write instead of to flush the socket every time we write a couple bytes for better performance.
Interesting will be to see the metrics from PMU to judge the cache utilization.
So are you saying that, okay, so I'm looking at PR 27176. So this is the staged message decoding and performance results. So what was the goal here?
I think its goal is to use stage to stage the decode phase of the messages.
And
so when the buffer is read from the wire and it submits the read buffers to the stage, and inside the stage the messenger will decode those buffers in a loop together, so it will increase instruction cache hit. So it is expect to do so.
Okay, I'll put some time to this tomorrow.
Sam, how's the Slim machine going?
Slowly, but actually pretty okay. So far, everything has slotted cleanly into definitely part of the peering machine or definitely part of PG. So that's nice. I'm maybe a quarter of the way through the total stuff, but that's probably misleading. I think it's going to get easier as I get towards the end because I'll find that I've already moved a lot of stuff over. The strategy essentially was to extract all of recovery state into its own file, mirror over the 47 state variables that define peering, your pure missings, pure infos, all that good stuff. And then map over every user of those state members.
And extract the interface into a separated abstract class.
Yeah, and so far it's been fairly straightforward. It's like the machine notifies PG of state changes like, I'm done flushing now, do what you need to do with that information, So it doesn't need to know about queues, it just needs to tell PG when events happen. Like, I'm active now, so good luck.
Okay.
So it's going okay so far. It's going to be a little while though.
Sure.
It's about half of PG though, so PG will be a lot smaller. That'll be nice. It'll make the compile units a little easier.
Yes, very good side effect. And Yingxing, how's your messenger going?
Okay, I will share my screen now. Did you see it? Can you see it?
I can.
Okay, this is pretty much what I'm doing this week is to try to apply the staging optimization to the messenger, especially the decoding phase. So in a very simple illustration, a message will be send, encode, write, read, decode, dispatch. A message will be have these 6 tasks in different components. So can you see it?
Yes.
Okay. So it's very simple. And in reality, if we have many messages, we will have multiple tasks scheduled in the messenger or in the reactors. So what we are doing is if we don't use execution stage, if we just submit the SeaStor tasks into reactors, it will be just run one after one in the reactor queue. And after we implement some stage, we can submit the related tasks into the same stage. So when the reactor is running, it will run the stage, and the stage will run the in-queued tasks together. And that's why we will have less instruction misses. And that's the benefit of the stage. And I've implemented this in this PR 27176 and have some analysis from the metric, the SeaStor metric collected from the SeaStor framework. And the result shows that the tasks, if we look at the task queue length, we will see with the staging, the task tends to be in-queued. The length is much longer than without staging. That's because with staging, the decoding task will be in-queued into reactor and into the stage. And when the queued cores reach certain threshold, the stage will flush, and that's why the queue length is longer here, and it is confirmed from the metric. But the result shows from the perf Crimson Messenger, it is not as expected with staging, because it seems to complete a million rounds of message, it will be slower than not staging. And then I looked at another metric, it records the task processed by the reactor. It shows that there will be much more tasks in the reactor than without staging. So I think that's a problem, because the stage will introduce much more tasks than before.
That's unintuitive to me. Why would it do that?
So I will explain it.
Cool.
So,
Yingxing, excuse me. So last page, can you go show the test result page?
yeah, this is the page.
Another is that there is a test result you give.
Oh, okay, result here is a round
so
1
that means
1 to
this
5.
Is the latency. The result is the latency.
This is the time to complete the 1 million rounds of message OP and OP replies from the client to server.
Okay.
It is implementing perf Crimson Messenger. If you can look at the code.
Yeah. So when you use the executing stage, the latency will be increased, and the throughput will be improved. So it's a balance between the latency and the throughput.
No. From from this result, this throughput is not better, it's worse. And,
staging it, but
yeah.
It's not throughput, it's latency. It's the time.
It's the time required to complete 1 million.
Yeah, it's the latency, right? It's the time to finish the 1 million request.
Yeah.
So that is the latency. Latency will be get worse, and the throughput will be increased.
Yeah, of course.
It's a balance between the latency and the throughput when you use the stage.
If you divide this by 1 million, you get the throughput. This is throughput.
Yeah.
So that is latency. Latency will be getting worse.
No.
The number of requests is the same, so latency is worse.
Yeah, latency is worse.
Yeah,
Latency
latency
is
will be
worse.
getting worse when you use stage. That is
And throughput is also worse.
Yeah, they're both.
Where is the
If you
throughput?
divide it by the number of requests.
So throughput and latency are the same here because it's not pipelined, right?
Throughput is the same, right?
No, I mean throughput and latency are the same metric here because it's not pipelined.
Yeah.
There's no queue depth here. So in this case, if it takes 0.6 seconds longer to do a million, it just means it took 20% more time,
Yeah,
or it went 20% slower.
It costs more time to send the same same number of messages, so that throughput is lower.
Which one means the throughput is lower? Which
Time.
number?
5.8 seconds versus 5.18 seconds.
Yeah, it's here. The not staging versus stage.
And I got a question for you. What's the payload of the message? What's the? I mean, if the decoding takes more CPU cycles, would that
the payload is okay
help with
here.
the test result?
Oh,
yeah, sorry.
I get it. Never mind. Sorry.
Okay, here and
explain.
okay.
The rounds is the request number, right?
Yeah, request number.
Yeah, but it's
so
the same.
They are the same request.
It's the same number of requests, just it just took a different amount of time to
So
complete.
they have the same how to say it? So you couldn't tell the throughput is getting worse.
You can, because it completed fewer of them in 5.18 seconds.
That's
correct. And if you cut the staging test off 0.6 seconds earlier, it wouldn't have completed as many. Throughput is lower.
No, because you use the same rounds, right? You give the same request number. If you not limited the request number,
then the non-staging one would have completed more by a factor of whatever, 15%, I guess. 10%. Anyway.
So, Chunmei, I think we can discuss later if you have some.
Yeah, so that means you send out the request and then you get the last one. So that totally time.
We can discuss later because okay. So let me explain it. So this is expectation as before that the tasks are queued in the reactors before staging is implemented. But the reality is not this.
Yeah, exactly.
It's because the read will return a ready future. It will directly call the decode, and then decode will call the SeaStor keep doing. It means that this loop may be in a single task. So it means that 4 and 5 are merged together with single tasks. And if we add a stage here to decode, the message we will force to split 4 and 5 into different tasks because so it is what stage is doing. It postpones the core of the code to the stage and store them as a task in SeaStor reactor. That causes the number of tasks increased a lot.
That's cool. So effectively, the problem is that read and decode are so cheap that the NQ-DQ time dominates. Oh, that's neat. Okay.
Okay. So the cost of scheduling will overwhelm the decoding effort. So here.
Yes, that's also my guess. We need to have a more complicated decoding to showcase the performance gain using staging design.
Yeah, so that's a fair point. You could pick one of the more obnoxious messages and encode and decode that instead. But my guess is that we're actually never going to find anything expensive enough for this to be worthwhile.
Yeah, so
but I could be wrong. It's
even the OSD ops.
Well,
I could be wrong, so it's worth doing the experiment.
There is also another factor in the equation, the size of your code. I guess, as far as I understood, the tests were made under a very small program. If it will change, if we get Crimson OSD instead of dedicated test case, it might be that the pollution of instruction cache so extensive that putting even more some extra efforts related to scheduling might be worth it. But it's just a guess. It needs verification.
It's also
it might be or might not.
There will be much more question marks tasks here. So if we have OSD, there will be much more different tasks in the reactor.
I'll point out that there's a fundamental trade-off though. So when you read and then immediately decode, the message data itself is still resident in cache. If you read a bunch of stuff and then decode a bunch of stuff, the message stuff may have been moved out of cache because you've lost temporal locality on the message bytes themselves, right? So it's a trade-off between instruction cache and data cache. So
exactly.
It's not clear to me what the answer is. Yeah, even in other words, even with a larger, I don't have a good model for it. I think Radislaw has a good point. It would probably be worth testing with a bigger message, but also we may just want to keep the patch series in our back pocket in case this becomes interesting later.
So from the analysis, I think the goal is to try to minimize task numbers to have less overhead, and because each task will be a lambda continuation and it needs some allocation from the memory, right? And
yes,
also
increase the length of backlog in a reactor.
Yeah, and we still need to improve instruction locality. So I think that's a point I still think application queue is worthwhile here.
So what is it that makes us think that instruction locality is the biggest point? The reason why I ask is because SeaStor seems to be deliberately designed actually to make instruction locality hard to achieve because you're doing your very best trade towards data locality. So do we have measurements that suggest that we're losing a lot of latency to that compared to other things? For instance, are we also getting extremely poor data cache hit rates?
I think it's a stage meant to be. It collects all the same tasks in the stage and run them together. So this increases the instructions together. So that's why the application queue can also increase the instruction locality because it queues the tasks in the application queue and runs the logic together here.
And also your implementation or your performance test does not enable the encryption. So in Nautilus we have encryption support. What if we have encryption enabled? That would showcase the performance gain using execution stage. Right.
Yeah, my point is application queue is to improve the instruction locality. Application queue is much similar than execution stage.
What does it do that's different?
It's just a simple queue, and for example, when we send a message, it first in queue to a simple F5 FO queue, and later the messenger will start a worker to consume the queue, but the worker will run and run and run, and when it starts to run, it will see a number of messages in the queue, so it can decode them together in a while loop.
So the observation is you get a smaller number of total tasks because the way it's implemented, you get one task per several logical messages.
Yeah.
Okay.
Yes, and the improved instruction locality is the same. And the queue is lock-free and share nothing because of SeaStor framework. Because previously we need to protect the queue with logs, but we don't have to in SeaStor.
So it wouldn't do anything to prevent it from thrashing
There's no other thread access.
The processor cache that is that might be caching the message contents. For small messages, that might matter, although it may not. I'm really not sure.
Okay, so Yeah, so the SeaStor task scheduling will schedule the workers of application queues, but not the actual tasks. So this means the number of tasks will be reduced a lot because it only schedule queue workers, not tasks.
Although I will note that that does
so that
potentially
is back to
latency,
the.
right?
Sorry.
Sorry.
Can you repeat?
So does SeaStar's scheduler have a notion of? Okay, I guess my concern is you schedule the decoding of a message that's ready to run and would ordinarily result in a fully synchronous execution path.
Mm-hmm.
It might get blocked behind something that needs to access cold memory or something, and it might not get actually executed for 3 or 4 tasks. That could be, well, it's still interesting behavior.
Mm-hmm.
Yeah, I don't know.
So let's go back to the previous discussion. If we use application queue or we use the reactor queue, reactor task schedule queue. If we use application queue, our code will do the schedule. It's our task to do the schedule. And
it's just a concept. The scheduling is just a concept, but it's just a simple queue to
do
the messages.
We implement the logic to do the dequeue and enqueue. If we use the reactor queue, we couldn't control it. So there are many additional instructions to do the scheduling and to arrange the tasks in the SeaStor.
There are some other ancillary sort of concerns. You're essentially creating a queue of queues, and you run the risk of these application queues becoming unbounded. So we'll have to be careful about that. That's sort of true no matter what we do, but it's just sort of a risk, or just a sort of thing to be aware of.
Yeah,
so instead of just having to worry about the number of reactor tasks there are, we also have to worry about the aggregate number of unprocessed application queue tasks. Might be worth doing. It's just sort of a thing. You see what I mean? Because eventually you have enough work outstanding that accepting more work from the wire won't speed the OSD up. So you have to.
You mean there will be much more latency? Or?
Well, it's okay. So we only ever want to accept as much work from the network as we need to fully saturate the storage. If the storage can process, let's say, 1,000 IOPS, although I know that's wildly low, then accepting 2,000 IOs from the network just wastes memory. We don't go any faster than if we just accept
it can be solved from some other utilities from SeaStor, like semaphore.
I know. I'm just stating that by adding the application layer, we have to be careful of that later. It's not really a reason not to do it. It's just sort of an additional complication. Keeping just a flat, I guess it goes back to the question of how we want to represent op queues. So maybe that's just a thing to defer until we have a good answer on that.
Okay, so the idea of SeaStor is to control everything we have. That's why they move the context switch to users. They change to use user space context task scheduling and
yeah, sure.
And the application queue enables us to control how much tasks it is scheduling. The user space.
Yeah, no, we can definitely do it.
Yeah, okay, so
it's definitely solvable. I agree.
So Kefu, that's why I have another PR. We have discussed that a lot to introduce an application queue there to send the message, right? Do you remember?
Yes, and I suggest using execution stage to let the SeaStor to do the batching and.
Yeah, what I'm concerned is we will have the same result if we use staging. So if my solution was to introduce an application queue there and use and let encoding to consume the messages in the queue and then send the buffer. So
Actually, hang on. The metric you showed before, go back like 6 slides. I think I maybe misunderstood something.
Which slide?
Keep going. One more. Yeah, that one. Yeah. Okay, this is tasks processed, right? Not tasks in the queue.
Yeah, task processed.
So imagine that we don't build up that many tasks. I claim that we're going to get the same behavior with the application queue. And the reason is that even with staging, it's not producing an extra task every time it schedules a new one. It's measuring not how many tasks there are, it's measuring how many times it has to switch tasks. So if you go back or go forward 2 slides. Yep. Yeah, that one. We're going to get this behavior on the right. We're not going to get it with the application queue, right?
We will get in the.
It seems to me that once the read is complete, instead of immediately proceeding to decode, it'll get queued onto a queue, which sure is not something that.
I'm not quite sure if it can improve the performance,
well,
but we can.
It's just not clear to me how it solves this particular observation. So it would still be the case that once you finish reading a task or finish reading a message, instead of immediately proceeding to decode because it's ready, you're still going to chuck it back into a different queue, and then that task that was doing the read is going to show up as done, and then it's going to have to go do a scheduling action. So that part's not different.
Yeah, it will. If we use application queue here, it will read buffer and put the buffer into the queue and then read again.
Right. So if the observation here is that. Okay, so you're saying the difference is that it won't immediately schedule, it's going to read again in the same task.
Yeah, and there could be another worker to do the decoding things only.
So what about the case where it's just, where the number of IOs coming in is substantially below saturation? Wouldn't that increase latency?
No, it's, I think, from the
scheduling action between read and decode.
No, it's not a scheduling.
It's some pointer following, right? It's just that the reactor drops a finished task, goes to its queue, pulls the next one off the thing, which happens to be the very same message. Goes in, says, "Oh, I need to decode a message," and goes and decodes it. So it seems like those additional instructions that it has to execute.
If the overhead is not very high, the read will call the decode directly.
With application.
And it means the application queue will always have some one or two buffers in the list, and it will always be decoded right after that. So I think the latency will not be increased in this case.
So how is that different from staged?
The stage will be cut this into two different tasks, but the read will directly call decode, and it will decode in the same task.
With application queue.
So there is no chance that decode will jump in the between different reads and pollute your instruction cache.
Yeah.
Well, I'm more worried about the other. I'm more worried about the other direction. I'm worried that the logic it has to execute to prevent that from happening will slow down the case where decode really is the next thing you want to do.
This might be entirely true. Our decode is quite simple, so there is now, even if it jumps between some reads, it's not a big deal. But if the decode would be much more complicated, staging could change something. Well, but still, I guess it's here that making experiments here is everything.
No, it is, yeah. So let me ask you this. So staged and application queue, those are both components that exist within SeaStor, right?
No, application queue is just a concept.
So it's part of a PR you wrote?
It's just a queue with a worker.
So I can understand what the difference is, that's all.
application queue is just a concept. It means you just put a message into a SDG queue and then schedule a working to consume that queue.
Yeah, but mechanically here, a worker is just a future you schedule in the reactor that maintains a reference to that queue and shows up as ready every time that queue is not empty, right?
Yeah.
So I'm wondering how staged works. That seems to me how I would assume staged works, which is why I'm confused.
Okay, I think the difference here is one consuming the task, the queue items. The application queue will do it in one task, but staging will have multiple tasks, one queue item for each task, because we submit to stage for each item. That's also why I explained here why the number of tasks are.
Yeah, see, that's what I'm saying. I'm not sure that is the number of tasks. I think it's the number of task switches.
What do you mean by task switches?
See, the y-axis says reactor tasks processed.
Mm-hmm.
So does that mean the total number of tasks processed, or does it mean the total number of times it had to switch between tasks? Because they'd be different.
I'm not quite sure, but
if you had, so like imagine you had one task that stopped for I/O 10 times. Does that count as 10 on that graph, or just one? That's what I'm not sure of. I don't really expect to have an answer. I just wanted to compare the two implementations. I need to learn how SeaStor works, basically.
Okay, so
probably what's the metric you were using for the?
I'm finding the original graph here. Those
you could naively implement this staged behavior by doing exactly what you're describing with application queue.
It's a metric.
If that's
here.
not how it works, I would like to find out how it works. Yeah, see, that's what it says, tasks processed. And I don't know whether that means the total number of tasks that ever got submitted to the reactor, including ones that continued to execute for like an hour with thousands of I/O interruptions, or is it the number of times it switched between tasks because I/O stopped?
This needs to look at the implementation of how.
Yeah, exactly. The latter seems like a more interesting implementation to me, or at least that's the metric I would want to know.
Yeah, but I guess the most probably it will report the metric maybe one second, and it records the number of tasks processed in that second and report here.
No, I get it, but I'm saying that so if let's say you start a future, which is represented internally in SeaStor as a task, that actually never completes. It's just that it does a fixed amount of CPU overhead, it spends some I/O. Does a fixed amount of CPU overhead, it spends some I/O continuously for an hour. So does that count as one task processed at the very end just once? Or does it count as a whole bunch of tasks processed as it switched in and out of being runnable?
I'm not quite sure here.
Yeah, so that's what I'm saying. If staged works the way I would assume it does, then it would give rise to this behavior, even if it were implemented the way you're saying application queue should be. So I'm not sure if you've actually looked at the way stage was implemented. I'm assuming you have, which means my understanding is wrong.
Okay.
So I was wondering, so the PR that has the application queue implementation is just in the Ceph code base, or?
Yeah, in the base, I will show you. Here.
Ah, right. Okay. 26.
And the commit is here.
Sorry, I didn't mean to slide roll.
I'll paste here. So, okay, that's all from me.
Any questions or problems?
Two quick notes.
Redox.
Two quick notes.
Sorry,
One is... Oh, sorry, please continue.
sorry, I was just asking what you're going to say.
So we merged an optimization for SeaStor, but not for MemStor. It's about using STD parameterless comparator for structure. I guess we will need to backport your optimization to MemStor as well. I plan to make a commit, but if you want to take it, I'm also fine. Another thing is about profiling. It's about profiling classical OSD. I guess that for the number of placement groups for Crimson is not so important, but for classical OSD it really is. By default, you have 8, and this could prevent classical OSD for doing effective sharding. Sharding in classical OSD is placement group ID based, so we need to have enough number of placement group to make it fully operational, make it fully effective.
I was using 16 in my test. 16 placement.
That's
16
only if you
TG
have more than one worker queue thread, right? You're talking about the inside of the OSD sharding?
Yes.
If the idea is a one-to-one comparison with Crimson, wouldn't it would be better to just restrict it to a single thread, right?
Well, we could, but we lost a lot of fun related to blocking and switching inside OSD. I would go on defaults, but significantly increase the number of placement group for the pool we will be using in testing. In my local testing, I'm usually going with 128 placement groups per my testing pool, but even higher might be better.
Okay, so if we do that, if the assumption is that Crimson OSD is useful, then the outcome we would expect to see is that throughput is whatever it is for classic OSD, but that CPU usage per IOP is a lot higher, right? That would be the outcome.
Exactly, and we can very usually and very precisely measure it using perf, using a PMU.
Oh, the perf tool, not perf counters. Yeah, you're totally right. Okay, yeah, that's a good point. Forgot about that.
And moreover, you can use perf stat after starting. You can start observing a process in the middle of its lifetime. There is a switch called -p in perf. That allows you to join to existing process. So you could avoid, you can exclude the setup phase. But well, it can be made by just enlarging your time you are testing. Still, it's an alternative.
Okay. Redox, I missed what your point for when you were discussing the placement, the number of placement group for testing classic OSD. So what the suggestion was? I a little bit confused.
The higher the better. By default, if I recall correctly, by default there you will have only 8 placement grabs per pool. This number will prevent classical OSD for doing effective sharding. On default, classical OSD is using 16 TP OSD TPs, workers of the shared pool.
Okay, I will use like 16, 62 or 60 or sorry 32 or 16.4 for testing?
I would go with
1000 also.
well, I guess it's sky is the limit. I would go with 128.
Okay. Okay. I will post the details regarding to my test for your review as well.
Cool, works fine.
Thank you guys. Talk to you later.
See you later.
Yep.
Thanks.
See you.
Thank you.
Bye.
Bye.